So we got one other little issue to talk about. So going back to glucose for a minute. Glucose, we oxidized it. So through glycolysis, forming 2 pyruvates. So, and assuming we're doing aerobic respiration here, so we got some issues. Where does glycolysis take place? In the cytosol. But where does the TCA cycle and electron transport take place? In the mitochondria. So we got a problem. So all of the NADH I make, so as part of the TCA cycle, is made in the mitochondria. And it's already there, ready to participate in the electron transport chain. But I made some NADH back here in the cytosol as well. And it's not in the mitochondria. And so if I want it to also participate in the electron transport chain, to pass off its electrons as well, then I have to shuttle it into the mitochondria. There are 2 shuttles. So I was going to get crazy and make diagrams for both, and then I saw the malate aspartate shuttle, and I'm like, holy cow, I'm not making that diagram. So I don't know how important the diagram really is. I looked on the practice test that you guys were given and stuff like that, and I couldn't find anything where the diagram was that important. So that being said, though, I can't say for sure that you don't have to know it and the order of events and stuff like that. But one big take-home message that you really do need to know. So the glycerol phosphate shuttle, the NADH is actually converted into NAD in the cytosol. So, but it also converts then some glycerol, or makes some glycerol phosphate in the process, which actually can get shipped into the mitochondria. Problem is, NADH can't get shipped into the mitochondria all by itself. So what I do is I oxidize my NADH out in the cytosol, producing glycerol 3-phosphate. Glycerol 3-phosphate can get into the mitochondria. Then once it's in there, I will actually go and reconvert the glycerol phosphate back, but regenerating some in this case actually some FADH2 inside. So effectively, the net result is I've turned NADH in the cytosol into FADH2 inside now the mitochondrion. So is that good or bad? It's both. It's good because now I have something in the mitochondrion that can participate in the electron transport chain. What's the little bad side, though? Yeah, I've lost some energy. So FADH2 is only going to produce 1.5 ATPs, whereas the NADH I started with would have produced 2.5. So the other shuttle, the malate aspartate shuttle, is definitely more complex. So, and I definitely don't have all the steps memorized myself, FYI. So, but net result, big take home, the malate aspartate shuttle is that the NADH in the cytosol ends up as NADH in the mitochondrion as well. And again, it's not really transferred across the membrane. We turn the NADH into NAD+, so turning some malate into aspartate, which then crosses the membrane and so on and so forth. But net result, so as we oxidize the NADH in the cytosol, but then we reform some in the mitochondrion. But the net result is that NADH in the cytosol turns into NADH in the mitochondrion. We don't lose any of our energy, any of our ATP producing ability in this process. So depending on which shuttle you use, then your net ATP count, if you start from 1 glucose back in glycolysis, will be different just a little bit. So how many NADHs did we produce back in glycolysis? 2. And so in this case, if I go the malate aspartate shuttle, so how many ATPs will those 2 NADHs turn into after using the malate aspartate shuttle in the electron transport chain and ATP synthase? They'll turn into 5. So 2 NADHs, as long as they stay NADHs in the mitochondrion, they will equate into 5 ATPs. But with the glycerol phosphate shuttle, those 2 NADHs are going to turn into 2 FADH2s in the mitochondrion. How much ATP now? 3. So with the glycerol phosphate shuttle, we're going to get 2 less ATPs per glucose molecule. So counting ATPs is going to be a big important thing today. So we'll talk about it again in this context, but we'll talk about it even more so in beta oxidation shortly.